szloca.
This paper aims towards a framework for full 3D tracking system. In context of new media arts, it looks at how to obtain useful data from physical world to virtually represent and detect multiple moving objects or people and their pose in 3 dimensions through just a single RGB camera. This is done by using computer vision, a subset of artificial intelligence, and building on top of it. Inspired by the intention to track in large spaces to create interactive immersive installations and collaborative games, the final goal of the paper is also aimed towards integration with more artistic-friendly development environments, such as game engines as Unity, which enables and unlocks the potential to create for a huge number of demographics of developers.
Traditionally, when we think about human pose and position tracking, depth sensors such as Connect are a topmost pieces of hardware to use. However, these sensors are limited with a relatively very low range of view and limited capacity of maximum number of people which can be tracked. Some installations use multiple sensors to obtain tracking data. This also causes interference with play space as sensors need to be placed close and also makes it harder to create a full seamless experience. Using multiple number of these application-specific hardware also becomes expensive as the area expands. Other options include using LiDAR, which goes through a similar problem of being very expensive in terms of computation power and cost required to track and classify objects in large spaces. Some of the other experimented methods to track people and interactivity in a space includes bombarding users in space with additional hardware, which also forms some serious questions with onboarding and user experience.
The method and framework proposed in this paper does not require any hardware on the users and works through just video inputs, which can be obtained through a well-placed regular camera.
This enables the experiences to be much more accessible and deployable while reducing the cost significantly. The framework also surpasses the limitations of traditional sensors such as low field of view and limited number of tracked people. The method proposed in this paper to obtain 3-dimensional position doesn't rely on complex training of computer vision algorithms, but combines prior computer vision research and adds a capacity to represent z-depth. That is, to represent overall position in 3 axes from a 2D input source. The method works on shooting rays from the camera towards an aligned virtual plane, which provides the z-depth relative to detected screen space position. The angle between the screen space position and the camera position is used to compensate for the visual distortion which happens due to objects being far away in the video, which makes them look closer and tighter to each other than they are. This provides better accuracy in terms of both space position for faraway objects as well as near objects. This obtained z-depth is also further used to scale the detected skeletons to compensate for the visual perception in the video, which makes faraway things look smaller. The benefits of using this ray method is that it's able to obtain positions with very far away placed cameras as well. Few recently published researches utilizing computer vision are able to provide 3D positions of skeleton of multiple users through just a single camera. However, lacks data on covering large areas or from far away placed cameras, as a low-cost method to obtain 3D position may perform better in these scenarios and may provide better FPS. The paper also further looks at the state of the art in the field of vision and provides methods and prior researches which can be tangled together in ways to overcome each other's limitations,
Creating a full inventory for the framework,
providing 3D skeletons, tracking an object ID, depth estimation, and getting accurate mass for classification from just a video feed. This can be used to artistically process videos, create immersive performances, real-time interactive installations, and collaborative immersive games in large spaces with multiple users, and can make huge surfaces interactive without needing any additional hardware on the surface. The framework can be applied and has huge potential in other industries as well, such as transportation, pedestrian behavior understanding, sports, warehousing, robotics, and more.